Hello everyone, my name is Alireza Ranjbar and I'm happy to present to you our work about residual feedback learning for context manipulation tasks with uncertainty. I will first describe the motivation behind this work and then the impedance controller that we use for our manipulation tasks. And in the next part, which basically represent the core part of our work, I describe the so-called residual policies, followed by the workspace where we test our ideas and the experiments that we do. And finally, I end this presentation with the conclusions that we draw and possible future works that can follow. So to start with, generally speaking, we desire an optimal controller, and regardless of the problem scenario or the application we have at hand, our solution may lie somewhere between model-based or model-free approaches. Where purely model-based solutions are often more data efficient, but also biased to imperfect models. They incur more engineering costs, they need more engineering knowledge, but also often offer more guarantees, which is in contrast to model-free approaches usually. However, we already assume that we have a solution from this domain, and this solution is more or less available to us as a black box, and we are wondering how we can improve it. A very common scenario in such case is that we are probably still left with some tunable parameters that we can tune them, for example, the Bayesian optimization or other algorithms, or we may still try using more engineering knowledge, maybe take our hand inside this black box again, come back here and try our best to improve this controller. However, we assume that we have also done the best we could on this level also. So we either didn't have any tunable parameters to start with, or we have done the best we could to tune them. And we have also basically used all the engineering knowledge that was available to us. And this controller is now truly available as a black box, and we are wondering if we can improve it further, desirably beyond its underlying structure. Before talking about possible answers to this question, I would like to focus on this part in the following slides, because we basically first want to do the best we can here before thinking about how we are gonna improve it even further with what we are left with. So I said we have a context manipulation problem, as it is rather established that regulating mechanical impedance has far more importance than tracking motion or force trajectories in such context problems. And this is basically the main philosophy behind impedance controllers. They offer safer interactions with the environment. They handle instabilities better and more naturally, hence also the popularity for human-robot interaction. And the recent approaches have also made them more energy efficient. In our case, we build our work above a recently proposed manipulation framework, where one of the main ideas is that the complexity of the problem can be reduced significantly, and the search space of the parameter can also be reduced. And a graph-based scale formalism can allow one leverage a more modular usage of different skills for different manipulation tasks. Yet in our case, we resort to a finite state machine. And since our experimental scenario is about a peg insertion problem where the peg is already grasped, we have this behavior sequence where we first move to a pre-assumed hole position. We find contact using the peg, search for the hole, make some alignment, and proceed with insertion. And during this sequence, if any problem comes up, the state machine then proceeds to another state, which is responsible for reset or a recovery behavior. So coming back to the earlier question, we have now this solution available to us and completely tuned, and we are wondering how we can improve it even further. An algorithm that was proposed recently in this regard is the so-called residual policy learning. And the idea in this algorithm is quite simple, and that is we can use a reinforcement learning agent and superpose its actions with those of the upstream controller. So basically, this policy is responsible to compensate for the imperfections that come from the controller's actions. In our case, since we know the main challenge is about overcoming position uncertainty of the hole or orientation uncertainty of the hole, we allow this intervention only during these two states. However, in reality, when we wanted to implement this idea, we still had to take our hand inside this black box and inside this state machine to make some tweaks to actually make this algorithm be feasible. And the reason is the following. The reason is that the controller actually sees the intervention of the policy as an external perturbation and error, and will try its best to resist such external perturbation. So for example, if our true end effector is here, an ideal policy will apply a force that will try to move the end effector to this optimal position, but the controller that is not optimal may have a different goal to maintain, and this may result in a competition between the controller and the policy. In such scenario, one may instead suggest modifying the input of the controller that we call residual feedback learning now. So we may not necessarily have any knowledge about the input structure of the controller, but if we were going to assume, for example, it's about position, end effector position, or joint position, now the controller actually sees this so-called virtual position instead of the true position, and it will apply its force accordingly. However, this algorithm also doesn't come without any limitation, and the limitations of this algorithm basically originate from the fact that we are now limited to the output structure of the controller. So for example, if optimal actions to the environment involve non-smooth actions or sudden actions, we may not be able to promote them through the controller, because the controller has its own structure to enforce over the output. And this may either be too difficult or may not be possible at all to learn such behavior with this policy. So no surprise, one can, in such case, then suggest combining both algorithms that we call hybrid residual reinforcement learning, to basically use best of both worlds in this case. So to summarize, we have now these three algorithms, and we may not necessarily have any knowledge about the input or the output structure of the controller, and this controller is truly available to us as a black box. But if we were going to have such knowledge available to us, we could still exploit such yet more. And for example, here we could define the action space of the policy in range space, and using the Jacobians, map them to joint torque space, or define it in the end effector position space and map it to joint position space using forward and inverse kinematic to exploit such knowledge that we have available for this input structure. In our workspace, we use two Frank-chemical robots, and we already fixated the peg on one arm to leverage Quaker experiment, and used another arm to basically introduce the uncertainties that we expect in the environment. And we have a similar scenario also in simulation. And it is also important to note that in these physics engines, for such concave objects, concave geometries, a convex decomposition, as shown in this figure, also is necessary. So in our experiment, we also use yet another layer to ease our debugging and our sample complexity. That is the so-called adaptive curriculum. And the idea about this curriculum is the following, that we have 4 training environment and 4 evaluation environment. The training environment always start with this initial difficulty, and they increase the difficulty by this increment if the success rate is above this bound, and they decrease the difficulty by this increment if the success rate is below this bound. While on the other hand, the evaluation environments always have the constant difficulty. And here is also the architecture that we use for our policy, for our reinforcement learning policy. So moving forward to our experiments, this plot represents our evaluation within the evaluation environments, and the starting point for all plots represents the zero-shot evaluation of the controller without any reinforcement learning algorithm involved. So as you see here, for pure reinforcement learning, when we start applying basically the reinforcement learning algorithm, the initial policy is not good and the performance is quite bad, which the adaptive curriculum realizes in the beginning and decreases the difficulty until we gradually start seeing more reward and start learning more, and gradually also increase the difficulty while also being able to improve our performance. And this is the performance for residual policy learning and residual feedback learning, both of which illustrate the sample efficiency, but the residual feedback learning shows better performance for overcoming position uncertainty, while the residual policy learning illustrate better performance for overcoming orientation uncertainty. For end effector range and residual end effector position feedbacks, we didn't realize a considerable contribution. However, for the hybrid residual reinforcement learning algorithm, we basically see that we have obtained the superior performance in both cases. And in the next experiment, where we have both uncertainty types available, we also see the superior performance of hybrid residual reinforcement learning in this pink curve. And if we were going to basically learn such behavior without the curriculum, with the same algorithm, the learning curve would have looked like this blue curve, which is basically because not the environment is simply too difficult for the learner to observe any reward and learn anything. We also do another experiment to contrast residual feedback learning and residual policy learning better. And in this experiment, instead of contact forces or end effector position as input to our policy, we have these RGB inputs to our convolutional neural network policy, and we allow the intervention of the policy only during this state. In such case, we also, in this experiment, we also have two other parameters. One of them is the so-called buffer steps that represents the number of controller steps where at the end of this state, the controller is applied without any intervention of the policy. And this basically represents how much opportunity the controller is going to have to resist any external perturbation and error that may come, for example, with residual policies, as we see in this case. And another parameter that is basically the so-called strict condition. And this parameter also raises an error if the state machine realizes that it hasn't observed its goal end effector position for the page. We see better performance with residual feedback learning in such case, simply because this does not result in any competition between the controller and the reinforcement learning policy. Whereas for the residual policy learning, the controller, the more opportunity the controller has, the worse the performance would be, because the controller will have more opportunity to bring this peg to the goal that it has, and that goal is not as optimal as the one the reinforcement learning policy is actually trying to promote. So moving toward our hardware experiments, here, since we don't have parallel environments and we only have a single environment, we basically have a train time where our adaptive curriculum starts from this difficulty, this low difficulty, which results in this high success rate, and gradually increases the difficulty until basically our success rate also fluctuates, and it basically gradually learns according to the parameters that we have defined in the adaptive curriculum. For example, those parameters define the bounds in the success rate at train time, at which the difficulty in the training environment that you see basically here should change, either increase or decrease, as you see in this blue curve. And on the right figure, as we see, the performance of the learned policy is quite improved compared to the initial policy that we have. And to summarize, residual policy learning offers the advantage that you can apply actions directly to the environment, but also the controller will most likely resist them. The residual feedback learning doesn't have this drawback, but also is limited to the output structure of the controller. For example, sudden actions may not be possible, whereas hybrid residual reinforcement learning leverages basically best of both worlds. Can also, of course, be less sample efficient because the action space is larger. Advantages of adaptive curriculum and efficient improvement for industrial assembly with uncertainty is also evident in our work. Possible future works that can follow include better exploration strategies, more guarantees, improvement over the guarantees, trying to boost the sample efficiency yet further, and adversarial methods that can be used, for example, using these two robots, and sim-to-real transfer that was also left to future works in our case. With that, I'd like to thank you for your attention and goodbye.